Hello everyone. Welcome to today's workshop, IP SoC Design, Co-Verify, Co-Validate, Co-Everything in 90 minutes. The presenters for today's workshop are from Agnisys team, Nikita Gulia, Neena Chandawale, and Anupam Bakshi. So SoC projects are naturally complex and difficult to complete successfully in a short span of time. From the specification, architecture, RTL design, and software design to verification and validation, all the aspects are challenging. This workshop will focus on the challenges faced by designers, driven by the convergence of applications onto a single SoC design, and will suggest methodology improvements using a revolutionary multi-platform solution such as IDesignSpec NextGen for creating IPs, stitching them together into an SoC, building software and test sequences for the entire design, and then documenting it. So, Autumn, you can take over.
Welcome to today's tutorial on IP SoC design, co-verify, co-validate, co-everything in 90 minutes from Agnisys. Is rounded. Device typers, part of HSI, are tedious to create. They are written in C and assembly. Introduction to typical SoC. Now here you can see an embedded system. This is how a typical embedded system looks like and how the hardware and software interact. Now we have a single CPU. Of course, there can be multiple CPUs. In this case, we are taking example with single core CPU. There are few peripherals and some programmable slaves. The programmable slaves have their own registers and memories, which can be programmed, and they are connected via interconnect fabric, which could be AXI, AMBA bus. Also, there can be some low performance peripheral that are connected to APB bus via a bridge, and there would be dividing. There can be two components, hardware and software. Now let's look at the challenges faced in the design. Sometimes there is too much data, and there are thousands of 32-bit registers, and the register width can also range from 64-bit to 128 bits. Changes to data cause havoc. There's significant source of bugs, and reusing IP is also a challenge. Verification and validation challenges. Duplication of work across teams, rise in complexity of designs, inability to create same debug environment for multiple platforms, mismatch in specification and implementation. SoC design companies has increasing demands of design complexity and design performance, combining automation with flexibility to accommodate changes in subsystems across applications, driving down the cost of design for a better OI, shrinking market windows, boosting productivity of design teams to meet shorter market windows. So to overcome all these challenges, what does an ideal solution look like? Which has ease of generation, and generated code should not be encrypted, should provide appropriate error messages, ability to reuse IPs, customizing the design, configuring the design, easy mechanism for generating IP blocks, ability to handle different bus protocols, and handling metastability of multiple clock domain designs. Designs must be functionally safe and secure. The creation of correct by construction, reusable designs, and in a faster way. So introducing cross-platform IDE IDS-NG, where the first step, specification, can be written in the Microsoft Word, Excel, OpenOffice editor based GUI, and also it can take in a specification, import the specification, which may be in Word, Excel, or OpenOffice format. Then its sequence information can also be captured in IDesignSpec in the same IDS-NG GUI. And SystemRDL 2.0 editor is also supported in IDS-NG. Apart from that, specification can also be taken in YAML format. Now, once the specification is captured in IDS-NG editor, user can have various views of the same specification with the help of just a single click, such as register view, spreadsheet view, sequence view, param view, SystemRDL Python editor. IDS-NG further has Git integration feature where user can use pull, push, commit, and diff-like features. Then tickle-based configuration for customization of output. AI-based sequence detection is also part of IDS-NG. And SoCE for capturing the information of connection of block at the top level and automatically generating the top wrapper module. Capabilities of IDS-NG, which are Git integration, creates design specifications, error linking to specifications are highlighted, hints are provided while writing sequences, checkers, etc. Navigators such as hierarchy view and sequence view show all automated sequence that can be used. Single GUI for capturing all information related to the IP SoC. Property panel to give values to possible properties which can be applied to that component. Now, features which are available for designing. First is bus protocols. The RTL generated can support different bus protocols for high performance data transfer among the IPs. The protocols differentiate features such as pipelining, burst, and split transfer based on the bus protocol. The desired SoC bus can be selected using the configure button in the IDS-NG GUI. Such a window will appear where user can select any of these buses to generate the output. The buses which are supported are AMBA AHB, AMBA 3 AHB Lite, ABB, Avalon, AXI, AXI4 Full, SPI, I2C, Starlink, Wishbone, OCP. Multiple bus domain is also supported. User can select bus domain from the configuration setting in which the block or chip resides. The chip block register can be configured to reside in multiple bus domains. Here, suppose there is a block A, which has two registers under it, Reg A and Reg B. Reg A has AHB bus at the following address, and Reg B has AXI bus at the following address. Various domains, generally 2 or more, are described in bus domain template, as shown here, typically at the top of the document. Apart from various design features, another feature which I would like to cover here is functional safety. System is functioning correctly or not. Human errors, environmental stress, cosmic rays, and hardware failures should be handled properly if they occur in a design. Design should be addressed with mechanism to detect and correct the failures. So design methods in IDS that are offered for functional safety are TMR, which is triple modular redundancy, CRC, which is cyclic redundancy code, parity, sniffing engine. They are used for error detection mechanism, and SecDet, which is for error detection and correction mechanism. Apart from that, functional security. Security is one of the most important aspects of SoC's IPs in Internet of Things era. Securing the SoC's IP is critical for providing authentication, confidentiality, integrity, non-reproduction, and access control to the system. Chip design should be secured and protected, should not be affected by any misconfiguration at the designer's end. Design methods for security in IDS are lock register, protection in software interfaces, and advanced encryption standard AES. Now let's see how to design IP in IDS-NG. So as soon as IDS-NG application is open, such a GUI appears. And this is the specification toolbar. And this is the project explorer window where all the files will come up. In the specification toolbar, a template of a register can be selected. Here is the register specification, where in this template, all the information related to a register can be provided, such as the name of the register, the field name, the bits of the field, the hardware software access, description of the field. In case user wants to give its own address offset or customize this register to make it a special register, that can also be provided in the properties, provided property space here. Now the same register with the help of a button, just a click, can also be viewed in the spreadsheet view. And the specification will look like this, the same register information in the spreadsheet view. And then the user can generate various outputs from it, such as C header, mistressing, C test, system RDL, register sequences. This is a sample specification. So with the help of multiple such templates, a register specification can be created. This is a template for a block IP. Its name is Ethernet_IP, under which two registers resides, TX packet and RX packet, under which three fields resides, and this is their bit information, software hardware access information, and the default value. After creating the specification, user can go to the configuration setting windows. Here, user can select which output user wants to generate. Here in the RTL section, Verilog has been selected. In the verification section, UVM has been selected. In the header section, C has been selected. In the documentation, HTML has been selected. And in the standard section, IPExact has been selected. The next step is to go to the settings and select which bus protocol user wants to use to generate the output. Here, EMBA-XI has been selected. After that, generate button can be pressed and the following sample code will be generated for that specification. This is the snippet of the RTL code which will be generated. Here is the module for the IP block. Some of the parameters are defined here. Here are the input and output ports depending on the software and hardware access of the registers and the decode logic. And represented here is the UVM output, and it is the class is generated for the block, which is extended from UVM_edge_block, and both the register are instantiated here. This is the generated C header output in terms of union and structure, and the macros. Represented here is the HTML output for the specification. And IPExact standard format can also be generated. Moving on to auto-generated standard IPs. So IDS-NG has set of auto-generated IPs. You can also say a library of IPs which are ready to use. So IDS-NG can also be used to automatically generate standard IPs, fully verified and validated, and their APIs. Also provides add-in functionality of configurability and customizability. So suppose your timer IP has been selected. A window will appear where user can further customize the timer IP, which will be generated based on some generation parameters, and the specification will automatically be generated. Let's look this more details. So this is how a register specification will look like. It's automatically generated by setting generation parameters. So this is how all the templates based on the generation parameters, this is the register specification which will be created for the timer IP. This is the generated sample codes for the timer IP. This is the C sequence, which can also be generated. Moving on to the Smart IP integration and SoC assembly. SoCE, a flexible and customizable environment for design assembly, for creating, package, integrate, and reuse of IP and SoC FPGA. Generic standards compliant IP exact automatically generates integration logic components and subsystem, automatically creates appropriate files for design verification and software teams. It creates schematics for design analysis, runs design rule checks to ensure IP and SoC quality. So first, we've already seen the creation of the specification and generating various outputs from a single specification, such as RTL, UVM, C header, HTML. Now, here you can see all those specifications are fed into IDS-NG, and RTL output like system Verilog and Verilog are created. Now these outputs can further be given as input to SoC enterprise. SlipG IP generator IPs can also be given to SoC enterprise along with third-party IP exact. And with the help of SoC enterprise, the top-level Verilog, system Verilog, and IP exact can be generated automatically. Let's see in more details how. So integration using console. So this is the IDS-NG GUI. Here in the Project Explorer window, all the files are opened up. And in the right-hand side corner, there is a button console. As soon as you press on the console button, a console window opens up. When the user writes SoCE, so SoCE shell is activated. And when the help command is given, then all the switches, all the help switches, APIs are available here along with their description for creation of the top level wrapper connection information. APIs available for assembly. Following mentioned APIs can be either used in command mode or in a tickle script, which can be further used in GUI mode. The configuration APIs are like SoC_set to set any parameters, SoC_read to read any input file, the Verilog file, any RTL file. Creation IP APIs, SoC_create, SoC_add for creating and adding an instance into the top wrapper file. SoC_connect and promote for connecting two modules or two ports together. Graphical APIs, SoC_graph and save graph for the generation of a block connected block diagram in a graphical representation of all the connections. And generation APIs, SoC_generate to generate the output and the RTL and the wrapper connected file in the output as well. Features available for SoC level design. SoC assembly using IDS-NG supports architectural level chip assembly, ability to create and edit a design through script command line interface, automatically adds instances in the design, makes connection, restructures, etc. View the resulting schematic for analysis, runs checks and generate different output collaterals for design verification and software teams altogether, automatically generate major subsystem of an SoC design with the flexibility to customize or configure for accommodating changes. Features available for SoC level design, auto generation of bus aggregator. So suppose there is a top block which has two modules, IP block 1 and IP block 2. They both are on AHP bus and they have to be connected. So aggregation logic module will automatically be generated and the connection will be made in SoC enterprise. So this way, it is smart. And say if block 1 is on AHP bus and block 2 is on APB bus, then a bridge module will also be generated as a Verilog file, as well as the connection will also automatically take place in the top wrapper file. And in the generated block diagram, it will also be represented in the graph. Auto generation of mirrored blocks. Suppose there is a block 1 IP and block 2 IP, and they have to be connected amongst each other. All the ports in block 1 IP has to be connected with the ports in block 2 IP. This is also possible with the help of just one single API. So this is how a sample tickle script looks like. There are various APIs such as read, here, all the files are read into the system. Create to create various instances. You can also observe that apart from the APIs, there are several switches which helps in capturing more information, such as the size and the parameters, also the base and the bus information. And then all the connect information between the blocks is given. And finally, the graph is generated. So this is how a graph looks like. This is the block diagram with all the connections. If I zoom into this part, so we will see something like this, that all the block modules are represented here and all their connection information is represented. Here, you can see that this is the aggregation logic and the bridge, which is automatically generated by SoCE instantiated. The next step is functional verification. It automatically generates UVM RAL model and environment around it, such as this is the DUT and the RAL model, and bus agents, monitor sequences, driver, predictor, adapter are automatically generated. Let's see this in more details. Features available for register verification. It generates the complete UVM test bench, bus agents, monitors, drivers, adapter, predictor, sequencers, and sequences, as well as the makefile and verification plan. The UVM test bench is fully connected to the UVM reg model and DUT, providing you with a push button verification. It generates 100% functional coverage out of the box with register-focused coverage reports. Generate sequences for special registers, including log, shadow, alias, and interrupt register. Ability to import IP exact, system RDL, RALF, Word, Excel, CSV, or XML YAML. AMBA AHP, AMBA AHP3 Lite, AMBA APB, XI4 Full, XI4 Lite, and Wishbone are supported. Sample sequence. For lock register, various sequence classes are generated. One such UVM sequence is shown as below. This is the register specification in IDS-NG format. And this is the automatic generated sequence, which will, this is one of the sequence represented here in the snippet, which will give out 100% code coverage. And the formal verification, automatic generation of system Verilog properties and assertion to check the register access policies, etc. Top level file to bind the DUT RTL as well as third party design IPs with the assertion. Make file or tickle command script, a verification plan with ability to back annotate these formal results so that engineers can analyze the results, comprehensive C++ test for firmware and validation, types of checks generated, protocol compliance checking of standard buses, such as AMBA AHV, 3HV Lite, EPP proprietary EXI, check for repeat on address map and register. ARV formal supports the following special registers, such as lock register, shadow register, reset checks for all fields, where the reset value specified in the specification also holds true for DOT. So here is sample assertion. Assertion for verifying special register like lock register is as shown below. This is the specification in IDS-NG, and this is the assertion-based code which is generated. As you can see, property and between the property and end property. Now, moving on to a system verification and validation. So to test, verify a design against a given specification before the actual tape out to ensure functional correctness involves validating the chip in system level environment with real software running on the hardware. So this is the chip design and development life cycle, where first step is the specification, architecture, microarchitecture, then its RTL design is created. After that, physical design, and in parallel, verification, testing, and validation takes place. After that, the tape out and the chip in-house back from fabrication and volume shipment finally takes place. Automatic test generation. Process of sequence generation include positive and negative tests for different access types, positive and negative tests to check functionality of special register, including shadow, alias, and interrupt register. Test sequences can be customized to generate 100% functional coverage out of the box with register for focused coverage reports. So this is the typical diagram that depicts the system level validation environment. You can have a C and UVM mixed environment. If we take a look at layered view, it impacts the application software layer at top and hardware application layer at bottom. So we have a UVM environment. That is with the register layer. We have a CPU here where the C tests run and loaded into the CPU's memory. And after the CPU generates the bus transaction that writes on the IP level RTL. And also we have a synchronization block that basically synchronizes the UVM and C environment. C test can be used to test IPs in a CPU simulation environment and can be run on CPU that is connected to IPs. The tool environment generates and uses standard C test for a captured IP register map. These C based standard tests include random value test, walking one test, a write read zeros and one test, a special software register access test, special register like rock, shadow, alias, etc. Tests are generated, customized test with respect to supported properties. Now, C tests are a combination of read and write APIs to configure the register and validate its firmware macro. So here you can see these are customizable read-write APIs. Automatic verification. UVM test pins are generated automatically and tests from register map generated automatically. And you can also run custom sequences. So here, this snippet shows the verification environment generated by IDS-NG. We are targeting bus layer, a register IP layer, and hardware layer. IDS-NG automatically generates an IP verification environment from a golden specification and hooks up the user RTL with IDS wrapper. So the box here represented in orange, gray, and light gray components are automatically generated by the IP, and blue ones are user-defined RTL. Dotted line represents the SV transaction for event capturing at the checker. RegBus agent is a component that converts register level transaction to bus level transaction and vice versa. IDS-NG generates RegBus agents for all ARM buses, for example, AMBA, XI, AMBA, EPB, and AHB. IDS-NG generates a top-level wrapper that contains instances of IDS register block in user application logic. And also there is one more component, which is called a tapper interface that taps the hardware interface pins as shown in the diagram. Model updater updates the RAL model via tapper interface whenever the RTL is updated using hardware pins. IDS-NG checker is one of the essential features which enables user to generate custom checks from a single specification. It automatically translates the checker specification to system Verilog assertion code. Now, moving on to project weather station. So, whatever we've seen till now in this tutorial, let's see a practical application of such features. A weather station, which is the project is weather station. A weather station measures atmospheric parameters and shares this data over a communication interface. It typically has the following sensors: atmospheric pressure, BMP 280, wind velocity, tachometer pulses. So here, the pressure temperature sensor sends the information to I2C master interface, which further sends the information to SPI and UART with the help of SPI and UART to local display and serial terminal. Here, wind speed pulses can also be are sent to the GPIO interface, which in turn sends it to the timer, which for a particular time counts the pulses and further send it to the application logic for calculation of the wind speed. Functional description, wind speed sensor. The total time for a round will be TH into M into N, where TH is cycle time for timer, N is total number of pulses in a round, and M is recorded timer count between two pulses. And this is the formula used for calculating the wind velocity, which is there in the application logic. Atmospheric pressure. In the current design, the I2C interface is considered for the sensor and is programmed in pressure mode. Apart from that, SPI display to send the commands and data to the local display. UART terminal. The weather station data is shared over a UART interface with the external world. Following is the ASIC format. The slide here shows the directory structure represented in blue is automatically generated with the help of IDS-NG, and only this application logic in the gray color is this module is created by the user. So here you can see various IPs such as GPIO, timer, PIC, I2C, SPI, and UART. So all these directories contains the code for all these IPs, which are automatically generated with the help of slipg IP library available. Uh, Here is the top directory, which further has 3 directories under it. The IDS-NG file, it contains the references to each of these IPs and contains RTL files in IDS-NG directory is approximately 12,730 lines of code, which are automatically generated by the tool. And it also contains the tickle run file. When it runs, then the graph output is saved in SoC_graph folder, and the RTL or the wrapper module, the SV and the Verilog outputs are saved in the SoC_RTL directory. Details of standard IPs, a GPIO. So when you go in the specification toolbar and click on the slipg button and select the GPIO from the IP library, here are some of the generation parameters based on which the specification will be created. This is how it is highly customizable and configurable. So the bus interface selected here is APB for the project. Number of GPIO pins selected are 4. Number of input sources are 4. Interrupt generation with enable. Pins are configured as input edge detection mode. Can be used either in POSIX or NEGEDGE. A timer IP is also selected from the IP library, and these are all the generation parameters which are available, which a user can put the value according to its own specification to generate the timer IP. So customized with register to store result value, pulse count, and wind velocity. Bus interface is APB, which is taken here. Number of timer is 1. Number of input sources are 4. Width of the counter is 32-bit. Width of pre-scale register is 32-bit. Incrementing counter mode, running mode to count between 2 pulses. Interrupt generation with enable. Next, similarly, we have predefined PIC IP, and here are all its parameters. The bus interface taken here is also APB. Number of interrupt sources are 7. Software interface is 1. A vector addressing, interrupt clear functionality, interrupt clear bits are packed, handling pending interrupt request, usage of register read write, single source output, and priority detection. I2C. Data can be transferred per transaction, which is taken as 16, and size of slave address is taken here as 8. By default, interrupt generation is done by enable. I2C IP acts in receiving mode. Interrupt generation with enable SPI is configured in transmitting mode. 8 bits of transfer per character, even parity is used. One-stop bit detection and generation, UART is configured in transmitting mode. So those were all the IPs which will eventually create the .v file and the specification IDS-NG format for all the IPs. Now, top containing all the standard IPs. This is the top specification, which contains references to the standard IPs. RTL generated of this top is used as input while assembling designs at SoC level. You can see here there is a top under which GPIO timer has been instantiated 4 times here, and PIC, I2C, API, and UART have been referenced. Here, a new file top can be taken, and no need to create a huge specification. Just the path to that particular specification or that particular file of the another IP can simply be referenced into the top. and it would just go to the path and collect all the information. The RTL of the top specification looks like the following. This is the module top, which has bunch of the parameters. And then the ports of the GPIO ports are present. Timer instance, since timer is instantiated 4 times, then here are all the input output ports for timer. PIC ports, I2C ports, SPI ports, and UR ports are present here. And under the top, all the IPs are instantiated. GPIO, timer, all these IPs are instantiated under the top. Now, moving further for its connectivity, Tickle script for assembling design at SoC level. So SoC underscore read. So to read IPs or blocks in different formats like IP exact, RTL, IDS ported blocks. Here, the search path and minus file switch takes the information of which and INC dir takes all the information of where the files are kept, and here are all the Verilog files which are to be read by SoCE. And this is the application logic by the user. SoC Connect is also used here to create the template and instance like block interface, etc. Here the minus type is block and minus name is wrapper underscore top. Here is the switch port to define additional ports, and minus top, that means that this block is the top block. And with the switch bus, the bus of the top is also specified over here. Apart from that, to add an instance to an IP block whose template is already present in the memory, either by using read API or a create API. So next step is to SoC underscore add and SoC underscore connect to connect the instances of IPs blocks together within a container or connecting them with a container itself. Here you can see the GPIO interface takes in 4 sources from the tachometer present, and it generates 4 interrupts, of which further goes on to 4 different timer and the timer will then count the pulses and further gives out the information to the application logic. So for the connection of this connection to capture it in SoCE Tickle script, this is as simple as using the API SoC connect and then minus source and minus destination switches can be used, and the source and the destination can be provided over here. And automatically in the top, the connection will take place just with the help of simple command like such as this. Similarly, all the IPs, timer and I2CM, SPI, UR generates interrupt and sends it to the PIC. PIC further communicates with the CPU. All this interconnection between all these modules with the PIC can also be achieved with the help of SoC Connect, source and destination information API. This also shows the connection between similarly between all the IPs. Like the timer when connected to the app logic, it is represented here in the Tickle script. So when the file is generated, so this is how the generated wrapper file will look like. Where apart from the parameters and input output ports, all the IPs are instantiated, and also in case any aggregation or bridges are needed, that those will also be automatically inserted and instantiated. This is the sequence specification, calling standard reset APIs of APIs from top. So this is the sequence information captured in IDS-NG GUI. And these are the sequences written on the top. And as you can see here, the call API is also used. So here the sequences of the following IPs have been called, and write function has been used on various registers. So creating a top sequence, calling reset subsequence, and configuration APIs of IPs. So further loops are used, such as if loop, and for loops can also be used. While statement can also be used. So this is how sequence information can also be captured in IDS-NG to generate various C, UVM, SV outputs. So this is the list of the files which are automatically generated with IDS-NG for this project. There are about 44 files, and their approximate number of the line of code is also represented ahead of them, which will be generated in IDS-NG. And this is the generated schematic for the weather station project. Here is the graphical view of the connection of all the modules at the top level, which will look like. If we zoom into this particular section, then you will see that all the modules are appeared here, and all the connection information along with their pins and their name of their pins are described here. Also, this is the generated top level IP exact file. And finally, looking at the benefit, so easier handling of complex and large SoC design through tickle-like scripts and GUI. On-the-fly generation, IPs and subsystems are automatically generated with support for customization and configuration, unencrypted code, boosting productivity of SoC design teams significantly, leading to faster time to market for competitive advantage. Keeps the development cost lower, ensures that semiconductor companies meet the stringent time to market requirements for competitive advantage, reduces SoC design and development costs significantly.
Thank you for that presentation. We can move on to the live Q&A portion of this session.
Hi, can you hear me?
Yes, we can hear you.
Okay. I have 2 or 3 questions. One is that because I couldn't see the slide very clearly, can the verification component be generated also in E, in the E verification language from Cadence? Because everything is in system Verilog instead of that. Some of us prefer E.
So Priya, did you say E?
Yes, Cadence E, the SpecMan E.
Okay. So currently we don't do it. We don't support E language.
Yeah. Okay.
Is that something you're
I just
looking
wanted
for?
to. I'm not sure because we are switching to system Verilog, but we have lots of code in E, and we are doing it mixed, and so it's not so important probably. Probably in a year or two, we will be also going to system Verilog, so it's okay. One more thing I wanted to ask, these bus protocols, can they be changed a little bit? Like, can we configure them in the sense that can we add another signal, or because what we do is we put some ready states because we have sensors which take a long time to deliver our data. So we add a signal or two to, you know, or stretch the signal or stretch the clock or stuff like that. Also in, I think in the I2C, there's clock stretching, and we also do it with ABB. And so I'm curious if the tool can do that, or is it like you have to use it like it's in the box, like.
So hi Priya, yeah, it is possible. There are multiple properties for customization of the bus output. So there are various versions of the widget as well, the version of various buses where there can be multiple flopped stages, and depending on, you can change, you can customize the bus further. Yes. Like protection properties are also there. You wish to opt in, opt out for the protection and for capturing the errors. So yeah, it's possible.
Okay. Because yeah, okay, all right. And one thing more, like we have, so you can just do a verification component extra from. So we can do a verification component extra, and you don't have to do the VHDL design. So we can just do the verification also, right? This was also actually discussed in the chat, but I just wanted to confirm, right? So you can just do one part of the thing, and you don't have to like do everything together in one, like everything has not to be done in the tool, right?
Yeah, so the basic idea is that you can create the specification in one tool, and from the specification designing, from the designing part, you're you're also generating the verification and the validation from a single specification. So yeah, the basic idea is to minimize the time, the generation time, like creating for the single specification, creating all the environments. And yes, you can obviously choose which outputs you wish to generate.
Okay, thank you. Yeah, all right. Thanks. Yeah.
And
Hello, Nikita. Sorry.
Yes.
yep,
Can I go ahead?
yes.
Yes.
Yeah, my
So
question.
yeah, Bruce, I seen your questions on the negative test case scenarios. So for the shadow register, like there are two registers, as I mentioned. There's one original registers and one shadow register. And original register can be written and read individually, but the shadow register can only be read, but it cannot be written because data will be shadowed from the original register. So one scenario can be trying to write directly on the shadow register. In the alias register, always the hardware access is NA, so it's should not be there. So in case there can be a negative scenario, then in case there is the write operation taking place on the alias register. So
Okay, yeah. Another question is about the formal. Can you give some more details? What formal verification codes can be generated through this tool?
Yeah, so the formal environment, the formal code can be generated for a specification, and it will contain the information about the register, their access, and the buses in form of assertion. But for more details, Neena, can you provide a link in our chat box for more details on ARV formal?
Yeah, I'll do it.
Thank you. So just now I remember in the slide it only mentioned the formal verification for registers, right? So I want to know if any other formal verification, let's say items or apps can be other items can be generated too. For example, or for example, we have the formal verification for to compare the RTL versus some model, or the formal verification mainly using the assertions, right? Or for the connectivity, there are many types of formal. Yeah, so I want to know what types of formal are now supported by your tool.
So it is like an assertion-based output which will be generated, and it will be typically based on the RTL, on the lines of RTL which will be generated, and the bus which is selected in case repeat is there on the register or not, and on the special register scenario. Maybe we can forward you one example and the expected output which we generate. If you can just provide your email ID to us, if you mind sharing it with us. We are free to like take it forward, discuss it with you, maybe send you a sample code for what we generate if it helps.
Sure, maybe offline I can give you my email, or so maybe yeah, some demo, if you have some demo examples, that will be very helpful. Yeah, thanks a lot.
Okay, sure.
Hi, Nikita, can I go next?
Yeah, sure.
So I noticed in your presentation that you have a couple of standard bus protocols that you guys support, right? So anything outside of that is out of scope for the tool, or how does that work? So suppose we have some other protocol that we want to test out.
So there is proprietary option which is given, to which user can connect their own custom bus to the logic which is generated. So will that help?
I'm actually interested more from a UVM environment perspective. So I'm talking more from the verification perspective. So I just wanted to know if, in case we have a proprietary interface, will the tool support the verification environment? Will it generate the verification environment for that particular case, or how would the tool handle such a scenario?
So since it will be a custom case, so we might be able to generate the common elements, but not the bus specific details of the UVM. That the tool is flexible, that there is a ticketing system, and if there is a requirement, like if you choose to generate the output with the tool and you have a specific custom bus, and so we are ready to take in that requirement and then implement that in the tool, and to help you out with that. Neena, would you like to add on it?
So yeah, Nikita, as you mentioned, I think we can do with the custom bus, but if you could share us the bus details, we can check at our end and can send you some examples.
Yeah, it was just a question. So yeah, I wanted to get a fairer understanding of the tool. And the other question I had was, does the tool also generate the sequences and the tests for that particular IP, or uh, does it ensure full functional coverage and all of those aspects, or how does that go?
Yes, tool it does generate automatic sequences, and will also generate 100% coverage report, and you can view that report in HTML format as well. There are multiple tests written for all the combination of hardware and software accesses, various like interrupts and counters, and readily used properties which there are. Um, Still, if in case there is a very specific scenario, and very like having no special register, or like it is very custom, then there is another tool which I mentioned about the IDesignSpec, in which user can also write its own sequences in our API in a very simple terms in a tabular form, and then there its specific sequences and UVM can also be generated, and they can also be used. So we also generate automatically, and we try to cover everything, but still sometimes there is some specific sequences and very design related, which you do not want to disclose. So in that case, you can write your own sequences and also generate the outputs. And you would be glad to know that you can also write your sequences in simple English language, and automatically the tool, with the help of AI technique, can also generate the UVM outputs.
Thanks, Nikita.